Welcome again to our lecture course on Relativity and Cosmology. So after having finished last time the mathematics, the new chapter on differential geometry, we are now ready to plunge into physics. So two central chapters, 11 and 12. 11 is about relativistic stars and black holes, and 12 about cosmology. There we will really see general relativity in action, because we cannot even attempt to understand such objects without using general relativity. But before doing that, we proceed step by step, and I first repeat very briefly the physics of ordinary stars, and then I will present the elementary theory of degenerate stars. There and you will see white dwarfs and neutron stars, before then going to black holes. Now for ordinary stars, and this is what I explain now, one usually starts by discussing the so-called hydrostatic equilibrium of normal stars, like our Sun. So stars on the main sequence in the Hertzsprung-Russell diagram in Newtonian theory. So we have here a cross-section, so such a star, and it's spherically symmetric. So this shaded region is a cross-section through a volume element, and you have here the sides dr, and then the area is dA. And we have, of course, here a force given by the pressure of the material in the star. So this is gas and radiation pressure for ordinary stars. The gas pressure is dominating. So here P is the pressure. So gas plus radiation pressure. And so here we have a force P of R dA. And here we have a smaller force indicated by the smaller arrow P of R plus R dA, because the pressure decreases, from the center to the boundary of the star. Now, considering this volume element, we can consider the force difference, which is, this minus this. So we have P of R dA minus P of R plus dr dA, and of course you expand this in terms of a Taylor series, so you get here, this is then minus P prime of R dr dA. So P prime is negative because the pressure decreases, so this here is positive. And so we have here, this is minus, or can write this as minus dP times dA. Now, of course, a star is an equilibrium if it's on my main sequence. So, which means that the outward pointing pressure force should be compensated by another force, and this is, of course, the gravitational force that points inwards. So the equilibrium. So we have the outward pointing pressure force is compensated by the inward pointing gravitational force. And of course you know from Newtonian theory how the gravitational force looks like, just from the inverse square law. So we have here this, so minus dP times dA must be equal to, the gravitational interaction, the gravitational acceleration G of R times dm, where this is the mass element that is contained here in this volume element. And of course we can insert here the corresponding expression, so you know that the gravitational acceleration is the inverse square expression G times m of R over R squared. And we can also write the dm as density times volume. So this is a rho of R times dA times dr. No? So you see here that the dA cancels, and we have here a differential equation with respect to the radial distance. So from this then here we get that dp of R over dr is a minus g times m of R R squared times rho of R. When you could also write it as minus g of R times rho of R. So that's a central equation in astrophysics that everyone who starts learning about stars encounters. So that's the equation of the hydrostatic equilibrium. So this is the equation of hydrostatic equilibrium. I mean, this m of R is of course the mass that is in the volume element, and it's written in Newtonian series 4 pi integral from 0 to R dr tilde times R tilde squared times rho of R tilde. No? So you have here, I mean, the spherical symmetry, and so the radius of the star is, say, R, and here m of R. Okay, m of R actually is the mass of the star up to that radius. No? So m of R is the mass of the star up to radius R. Well, that's the meaning of this m of R. So the pressure, of course, decreases with increasing R. This is the Newtonian expression. We shall derive the general relativistic expression in the next section 11.2, after having discussed the theory of the degenerate stars. Okay, that's the first subject section. The second one is on some heuristic considerations. And these heuristic considerations, they aim at connecting, say, the physics of the stars to the size of general relativistic effects. Let me choose, for simplicity, and this is sufficient for this consideration, constant density, which is of course not realistic, but gives you correct order of magnitude. And so you get from this that dp of R over dr is a minus g m of R over R squared, and then you have the constant density rho, and so you can here also then introduce the m of R. So here we have the m of R is then 4 pi 3 over times rho R cube. No, it's because rho is constant, so it's just the mass that is here in that ball is 4 pi 3, the usual expression here, rho R squared, rho R cube. And this gives then minus 4 pi over 3 g times rho squared times R. Now, this is a simple differential equation that you can immediately integrate. Yeah, you see dp over dr is proportional to R, so these are constants. So p is proportional to R squared naturally, and so you get from this that p of R is p of 0 minus 2 pi over 3 g rho squared R squared. And okay, P 0 there, so this is the pressure at the center of the star, and we call this P, or we call this P naught. This is the pressure at the stellar center. Okay, that's of course an unknown, but there's also another boundary condition. If we are the surface of the star, of course, the pressure should be 0, because the outside, certainly there's vacuum, there is no material. So we have here the vanishing pressure at the stellar surface, which means P of R is 0. And okay, if you insert this here, that P of R is 0, that means then you insert here capital R squared, and then you have a relation between P naught and the radius of the star. So from this then you get that P naught is 2 pi over 3 G rho squared R squared. That's, I mean, a simple relation between, I mean, the radius of the star and the central pressure. Let us for the following have a look at the physical dimensions of the quantity. Of course, you know that the dimension of pressure is force over area. So this is mass times length over t squared. Okay, the dimension of the mass density rho is mass over length cube, which is the same as the dimension of P over length squared over t squared. So you see here, this differs from the dimension of P by a velocity squared. So we can form a dimensionless quantity, and this is P naught over rho c squared, with c being the speed of light, which is of course a natural velocity that we have here. So this is dimensionless, and if we then use this here, this relation P naught is proportional to r squared, we get that this is 2 pi over 3 G rho r squared over c squared. Now recall that from earlier discussions that we introduced the so-called Schwarzschild radius in connection with the Schwarzschild solution. So we call, I mean, Rs, which is 2 gm over c squared, Schwarzschild radius. And let's also insert here rho is m over 4 pi over 3 times r cube. Okay, here I should write this down. So this is m over 4 pi 3 r cube. So we get here that this is Rs over 4r. So this dimensionless ratio here is related, I mean, to the geometrically, basically to the ratio of Schwarzschild radius to stellar radius. Now, of course, this factor 4 should not be taken literally, because this is just an estimate. So, but what we get from this here is an order of magnitude relation, which means that the pressure over rho c squared, so it's not a central pressure but an average pressure, should be of the order of gm r c squared. So as you recall, this is important in general relativity. I mean, the effects that we derive for the solar system, they were of this order. And you see this ratio is actually determined by physical parameters of the star, namely the pressure and the density. So if you have a higher pressure, then you see it's more relativistic. Now this ratio here will appear frequently in the following discussion, so let us give it a special name. It's a function that depends on rho and also the temperature, because this is determined thermodynamically, and we call this an equation of state. The equation of state means, I mean, the pressure is a certain function of the density and the temperature. I mean, you know that from thermodynamics. Okay, before we go to the degenerate stars, let us first go to the normal stars. with the equation of state. So this is then here A, so these are the normal stars. Think at our sun, if you want to have an example here. And for the normal stars, the first approximation we can use for the equation of state, the equation for an ideal gas. That gives a good estimate. So we have here an ideal gas, and you know the equation of state, it's pressure times volume is N kBT. Where this is the number of molecules in the volume V. You can also write it in terms of Avogadro number and the like. I don't have to write this down. So if you insert this here into this equation, then you get that F of rho and T, which is P over rho C squared, this is N over rho V times KB T over C squared. Now rho times V over N is the dimension of a mass, and it's the mass of the molecules that are the building blocks of the gas. So here, I mean, M rho V over M is the molecular mass. Well, later it will become the proton mass. So let me just call it M, and then it's a kB T over M C squared. Now, so you see this ratio is given by this thermal energy over the rest mass energy. Now let us go back to the estimate here. I mean, we have to set this equal to the right hand side. So we have here then G M over RC squared is then of the order of kB T over MC squared. Now, where does this kBT, how is this determined? Well, according to test statistical physics, this comes, of course, from the kinetic energy of the molecules. So recall from statistical mechanics that, I mean, there we have 3/2 kBT for the 3 dimensions. You can set as 1/2 mv squared, which is the average molecule velocity. So that from this you get then kBT over mc squared is then v squared over 3c squared. Okay, this is 1/3 v over c squared. So that in a sense is a factor from special relativity, but I mean, for normal stars, of course, velocities are much smaller than speed of light. But you see here how also these special relativistic effects enter. Now, but how can we estimate this? Of course, the mass here is, well, you can insert the proton mass that's dominating, and when you have envisaged the sun, it's mostly, I mean, hydrogen and helium, and this is of the order of giga-electron volts. Now the kBT, this comes from nuclear reactions, and if you ask the nuclear physicist or read in your earlier nuclear physics scripts, this is kilo-electron volt. Yeah. So here the kBT over mc squared, this is the order of kilo electron volt over giga electron volt. No? So that's here is the rest energy of hydrogen, and this here is from the nuclear reactions. So you have to understand nuclear physics to get this, and of course this is here roughly 10 to the minus 6. And you know that 10 to the minus 6 is the order of relativistic effects near the sun. No? If you recall the redshift and mainly or even more the deflection of light, also perihelion motion of Mercury, then we got this typical number 10 to the minus 6. And you see that does not come, say, from the size of the star. It comes from the physics of the interior of the star that determines. No, if you can have a bigger star, but as long as you have this ratio, I mean, you have the same effect. No? So nuclear energy or energies from nuclear reactions over rest mass of the hydrogen. This is what determines general relativistic effects. No? So this is the order of GR effects. So recall from our chapter 9 where we had all the effects. So the smallness of these effects is due to nuclear physics. Yeah? That's the message here. Now let us leave now the ordinary normal stars and go to the, for us, more interesting objects, namely white dwarfs and neutron stars, and they are examples of so-called degenerate matter. So in the following I will first discuss in general some equations for degenerate matter, and then I will first apply it to the situation of the white dwarfs, and then for the neutron stars. Okay. So after having dealt with a brief introduction into the physics of ordinary stars, I mean the equilibrium, let us now go to what interests us more, degenerate matter. So part B here is a general discussion, I mean very brief and elementary, and then C and D will be the concrete cases of white dwarfs and black hole. So after nuclear fuel is exhausted, then the star collapses, and so for some region has no equilibrium, but a new equilibrium forms, and this is the so-called degenerate matter. So for rho bigger than 10 to the 4 gram per cubic centimeter, of course we take these results from astrophysics. So we have so-called degenerate matter, where we have, I mean, this P of rho c squared is a function that depends only on rho, so independent of the temperature, although the objects may have a temperature. Now a heuristic derivation of this, and the exact derivation is found in textbooks of statistical mechanics. So let us have the uncertainty relation, so the momentum, which are called PF, times D is of the order of h bar. Now, that means that actually this degeneracy comes from the pressure that is exerted by electrons, which are quantum mechanical effects, and due to the Pauli principle cannot be confined to arbitrary small distance. So it's an effect that comes from fermions. So this we call the Fermi momentum, and this is just an order of magnitude estimates. It means that electrons are confined to a region with volume of the order d cubed, so to a certain volume, and we neglect factors, and this of course comes from the Pauli principle. And so non-relativistically, there's an energy, of course, connected with this momentum, and this is we call EF, which is PF squared over 2 ME, and this is the so-called Fermi energy. And here we have the electron mass instead of the proton mass, although the proton mass dominates, but of course here this is in the denominator, so the smaller mass dominates here. Of course, quite generally, electrons can also have a high speed, so we need to use, the general relativistic expressions for that. So, we had for the ordinary star, we had that F is which is given by P over rho c squared, is of the order of kBT over mc squared. Now, heuristically, we replace this thermal energy by the Fermi energy, because this here is the relevant energy. So this here replaced by epsilon f. But now using the general relativistic expression, so we have f is then 1 over mc squared, and then we have the this here, but the special relativistic expression pf squared c squared plus me squared c to the fourth minus me c squared. Of course, of interest are the limits, the non-relativistic limit and the ultra-relativistic limit. So, and here this will be, without index, will be the proton mass. I could add here p, but I just keep that here as it is. So here, that is, depend for the non-relativistic limit, of course, this here dominates. And so here we have, this is 1 over mc squared pf squared over me. So this is the non-relativistic limit, and which corresponds to this here. And the relativistic limit is where this dominates here, and the rest mass is fully negligible. We have 1 over mc squared pf times c, which is ultra relativistic limit. And for the exact case, of course, you have to evaluate at square root. And it's clear, you have here a transition at roughly pf is me times c. Now, if you insert here pf, mc, then these are identical. So the transition at pf order of the magnitude me times c. Now, if you go back here to that estimate here from the uncertainty relation, so you have here then that for the transition here you have, d is h bar over pf, and if you have the transition here, we have d is of the order of h bar over me times c, which is a well-known quantity in atomic physics. It's the Compton wavelength, or more precisely the reduced Compton wavelength, which for the electron is around 4 times 10 to the minus 11 centimeter. So that's the reduced Compton wavelength. And of course this corresponds then to a certain density of mass over the cube of this. So the this corresponds to a density rho naught, which is the mass now of the protons, because they dominate the mass, over this cube, which is around 3.3 times 10 to the 7 gram per cubic centimeter. So that's a critical density that characterizes, this transition into the ultra-relativistic regime. We can also rewrite this as follows. So having, pf of the order of h bar over d, and d is of the order of m over rho to the 1/3. So we get from this that pf is of the order h bar rho over m to the 1/3, so that we find from this here, and we are only interested into the in the two limits. So from this we get then that f, which is p over rho c squared, is of the order of me over m rho over rho naught to the 2/3. For rho smaller, roughly, than rho naught, so that's a non-relativistic case. Or that's here from the second, you have me over m rho over rho naught to the 1/3, which is a rho bigger roughly than rho naught, and this is the relativistic case. No? So that's important, because you see here, the two different exponents here. Now, p over rho c squared is proportional to rho to the 2/3 in the non-relativistic limit, but relativistically it has here the power 1/3. And this gives, actually, as you will see in a minute, rise to the existence of white dwarfs. Here, this relativistic effects. Okay, so this is valid in a regime between 10 to the 4 gram per cubic centimeter and 10 to the 8. So then for even higher densities there will be an unstable region, and then a new equilibrium with neutron degeneracy. Okay, this is an elementary heuristic consideration, just to give you some intuition. The exact treatment you get from statistical mechanics, and in almost every text on statistical mechanics textbooks you find the derivation, and I will not repeat it here. So exact treatment from statistical mechanics, and already in the classic books by Landau and Lifshitz, volume probably 5 or so, you find this, and what you find there is the expression p over rho c squared, this 3 pi squared over 2/3 over 5. I mean, for the non-relativistic limit, that's no, so e.g. non-relativistic limit. And then you have me over m rho over rho naught to the 2/3. So you see here, if you compare our estimate here, then you see this is not bad, this estimate. I mean, there's a numerical factor which is around 1.9, but apart from that, this is what we already get. Yeah, so just from the physics and from the order of magnitude and the dimensional arguments. And a similar follows also for that here. So we are in a good shape, so we can use with confidence these expressions. They are justified by statistical mechanics. Okay, so that was B, I mean the general part. Now C is devoted to the white dwarfs. No? So recall we had, I mean, Gm over Rc squared, which is P over rho c squared, which is F of rho. We want to get now some insight into the possible mass range and also the size of objects that are equilibrated by electron degeneracy pressure. So if we have here R, we can write as, of course, mass over density to the 1/3. And if we insert that here, then we get so from this, then if you insert this here, here this R, then you get here, you can solve for m. So this is simple to do, and you get c cube f to the 3/2 of rho over rho to the 1/2 g to the 3/2. No, so that's depends only on rho, and this is why we can write it as an m of rho of the density. So m and rho are, or m of rho and rho are connected. No? So that's for a degenerate star equilibrium, you have this relation between mass and density. Now we have to insert here F, of course, here from here. No? So that's what us gives then here the direct relation between m and rho. Okay, so this is from insert from above. And let us treat differently the non-relativistic case and the ultra-relativistic case. So first the non-relativistic case. So we have then f of rho is me over m rho over rho naught to the 2/3. And if you do that, I mean, then you get an expression for m of rho, which is easily written down as c cube over rho to the 1/2, g to the 3/2, and then you have here rho to the rho naught, and you have me over m to the 3/2, which you can write as this as, okay, rho over rho half gives you rho half, so you can write this as rho over rho naught to the 1/2, which is dimensionless, times, and the rest must be a mass, and it gets a name n capital C. So this is for rho smaller than this transition density to the relativistic regime. So here m of rho is rho to the 1/2 times this mass mc, and let me write down this mass mc. So mc, which is defined as m of rho naught, and rho naught is m over Compton wavelengths cube. So this is c cube over rho naught to the 1/2 g to the 3/2 times me over m to the 3/2, and it has a name. It's called after the famous person who first derived these expressions, Chandrasekhar from India, who found these results when he was at very young age traveling by ship from India to Britain. So at that time, of course, travel was very long, and so he had time to work. So this is called the Chandrasekhar mass. Chandrasekhar mass, and it's a central quantity in astrophysics. Now, for the relativistic case, or relativistic limit, there we have f of rho is me over m rho to rho naught to the 1/3 instead of the 2, right? And if you then calculate the m of rho, because of that different power here, 1, the rho's cancel out here, and in fact m of rho is a constant. It's mc for rho bigger than rho naught. No? So there is no rho dependence, and which means that once by collapse the star gets to the limit where the electrons move relativistically, the mass does no longer change, and it's equal to the Chandrasekhar mass, and this object we call a white dwarf. Object that realizes this case is called a white dwarf. Well, after its appearance, I mean, these are end results of stellar collapse of ordinary stars. So also our sun will experience once in the future the fate of collapsing to a white dwarf. And this white means that it appears white because of the temperature it has, and dwarf you will see when we estimate the radius, because it will be very small. Okay, if we use m over Compton cube, is we insert the expression for the Compton wavelengths. We have m times me cube c cube over h bar cube. Then we can write in mc, which is defined here in a more suggestive way. So we can write then mc is m times h bar c over m squared g to the 3/2. okay, this has dimension of the mass, it's the proton mass, so this is dimensionless. And this dimensionless number we can give a name. It's m times quantity alpha g to the minus 3/2. Now alpha g is defined as g m squared over hc. You can also write this as m over the so-called Planck mass squared. I mean, m squared and h bar c over g is then also a mass squared that we call the Planck mass squared, which plays a role in, I mean, combining quantum theory with gravity. So that's here, so-called Planck mass. And so this is a dimensionless number, and if you insert here the values, it's 5.91 times 10 to the minus 39. So that's a very small number, because this somehow resembles the fine structure constant in electrodynamics, which is E squared over h bar c. So instead of gm squared, you have E squared. It's sometimes called the fine structure constant of gravity, although this is a bit misleading name, but that's what you find. So fine structure constant of gravity. Yeah, if we go back here to this, of course, alpha g is very small. It has to do with the relative strength of electromagnetism and gravity. But this is very big, so this gives about 1.8 solar masses. Now that what we get as an estimate. Now a more precise calculation with all the prefactors and so gives a somewhat smaller mass of 1.44. If you use from statistical mechanics the correct expressions. But this is sufficient for our purpose. So more precise calculation has mc is roughly 1.44 solar masses. Now this alpha g is actually the central quantity that determines the size and the mass of stars. It depends on this ratio, which is an input from experiments. It may be derivable from a fundamental theory of all interactions, but so far it's not known how to calculate this number. It's an empirically determined number. Now we have to know what is the mass of the proton. Of course, we also have to know how strong the gravitational interaction is. But you see here from the occurrence of h bar that h bar is not only relevant for atoms but also for stars. It does not only give you the size of atoms, the Bohr radius and all that, it also gives you the mass scale of stars in the universe. So because the white dwarf results from the stellar collapse, say, of the sun, you could even get from just taking this to be one solar mass, a rather good estimate of Planck's constant, just from the mass of the sun. If you did not know anything else, just this, you could derive the Planck's constant from that. So that, you see, is a very exciting and important connection between the microscopic and the macroscopic, and tells you that they are not independent, that you cannot just discuss the microscopic forgetting about the macroscopic and so on. So h bar is relevant for the size and for the masses of the objects in astronomy. I would like also to give you the size of this. First, let me give you the number of protons. Number of protons in a white dwarf. So this stands for white dwarf. So A has we can estimate just by dividing, the mass over the proton mass. So which is alpha g to the minus 3/2, and this is around 10 twice 10 to the 57. And that's a good estimate, gives you also good correct order of magnitude for the number of particles in the sun, that the sun composes, number of protons. Of course, we also have the number of electrons, the same. Now the GR effects, they are of the order, I mean, as we, okay, it's written down above, but let me write it out again. P over rho c squared, so and this is me over m, and you have rho over rho naught, and either to the 2/3 or to the 1/3, depending on whether it's relativistic or non-relativistic. But you see, this is of the order of me over m, basically, if this is of the order 1. And so this is of the order, say, roughly 10 to the minus 4. I mean, we don't have any prefect, so numerical factors here. And so you see, above, for normal stars, or I should write normal stars, then we had kBt, and this is here replaced by me c squared. Yeah. So for the normal stars, this comes from nuclear physics, it determines relativistic effects to be 10 to the minus 6, and here we have mec squared over m squared, and gives a bigger number, 10 to the minus 4. So you see here, it's just a ratio of the masses that determines the size of relativistic effects. Now the radii of white dwarfs can also be estimated. So radii of the white dwarf, so r, okay, you have m over rho to the 1/3. So let us insert here then m of rho. I mean this expression here, so here m of rho with mc of rho over rho naught to the 1/2, and then you get order of magnitude m over rho to the 1/3, alpha g to the minus 1/2, rho to rho naught over 1/6. So and if you insert here that the mass is density rho naught times Compton wavelengths cube, we had, I mean, here this here is rho naught, then you get it's lambda e times alpha g to the minus 1/2 times rho naught over rho to 1/6. And if you insert numbers, this gives roughly 5,000 kilometers times rho naught over rho to the 1/6. So the radii you would expect to be of the order of a couple of thousand kilometers. Yeah, I mean, if this is of the order 1, and okay, if this rho approaches this, then you have this 5,000 kilometers, and this is more the size of the Earth than the size of the Sun. So the Sun has a radius of 700,000 kilometers, but if it has become, after it has become a white dwarf, then we estimate it's only a couple of thousand kilometers. And you can imagine how dense the matter is. Now that you cannot carry even, say, a small fraction in a matchbox of that matter. Yeah. So you can also introduce, I mean, the Chandrasekhar mass. So we get, you can easily from this expression get mr cube is of the order of mc times rc cube. I mean, rc is here that. And you see here, I mean, how important this alpha g is here in determining the size of this. So which means that the radii fall with the increasing mass. If this is a constant, so if this if the mass is bigger, then this would be smaller. So let me finally then address neutron stars. So astrophysical theory tells you that for densities above roughly 10 to the 8 gram per cubic centimeters, you will have a transition of this electronic degenerate state to neutron matter where I mean that the inverse neutron decay becomes important at these densities where protons and electrons actually combine to a neutron plus an electron neutrino. And if these densities are reached, the theory of degenerate neutrons tells you that we have the end of the transition and that we basically have converted all the electrons and protons to neutrons, and the resulting object we call a neutron stars. Now the calculation now of the equilibrium properties of neutron stars is very similar to the one above for the white dwarfs, because the neutrons are also fermions. They exert, according to the Pauli principle, a degeneracy pressure. So also all what we have to do is in the above expression to replace the electron mass by the neutron mass. No? So calculation similar to the case C, with ME replaced by the neutron mass. The neutron mass, is roughly equal to the proton mass. So we can set Mn roughly to m, and the result is then that our f of rho, which is p over rho squared. Recall here the expressions of f of rho, for example, here above. No? So you have here me over m, and this is replaced by mn over m, which is roughly 1, because we neglect the differences of neutron and proton mass. So this is then rho over rho 1 to n over 3, with n equals 2 for rho smaller than rho 1, so that's a non-relativistic case, and n equals 1 for rho bigger than rho 1. So you have here, that's important, I have to emphasize the factor 1 instead of me, what we had above, me over m. And so that gives the main difference between these objects. Okay, rho 1 is the analog of the rho naught here for neutrons. So rho 1 is then the mass of the neutron over the Compton wavelengths of the neutron cube, and this is of course this density is of course much bigger. This gives you this 10 to the 16 gram per cubic centimeter. No? So lambda n is the reduced Compton wavelengths of the neutron. So lambda n is roughly 2 times 10 to the minus 14 centimeter. And okay, the electron Compton wavelength was at the order of 4 times 10 to the minus 11 centimeter. So of course this is smaller by the factor of electron mass over neutron mass. Now the mass spectrum you get also, from using this result. So you have here m of rho is in the non-relativistic regime rho over rho 1 to the 1/2 times Chandrasekhar mass for rho smaller than rho 1, and it's a Chandrasekhar mass for rho bigger than rho 1. No? So the Chandrasekhar mass is the same. Actually, it's the same expression if you think about this quantity. It's just the proton mass times alpha g to the minus 3/2. So that's unchanged. So you would expect also these neutron stars to be of the order of the Chandrasekhar mass. Unfortunately, the details are here more complicated, because you have also details of nuclear physics that are not present in the case for the white dwarf. So you have to discuss really more in detail the nuclear equations of state. To have these processes under high pressure, and so this is difficult work. and I only have to refer here to specialized work in nuclear physics, and they teach us that, I mean, the mass that you can, I mean, the maximum mass that you can have is a bit above mc. No? So here, details of nuclear physics are important. So, and detailed studies lead to, okay, the mass of the neutron star is, okay, smaller than, I mean, roughly 3 solar masses. No? So it's a bit above the Chandrasekhar limit, so you can stabilize these objects at a somewhat higher mass. Okay, the order of relativistic effects, that's what we are interested in our lecture course. No? So Gm over Rc squared is the order of P over rho squared, and okay, now this is rho over rho 1 to the 2/3 or 1/3. So I mean, here of course we have this important, well, this is of order 1, but this here is the ratio of the masses, but here now we have neutron mass over proton mass, and this is of the order 1. No? So this is of order 1, which means that relativistic effects for neutrons are definitely non-negligible. Okay, if you calculate more precisely, they are maybe 1/10 or something like that. They are smaller than 1, but they are definitely there. So this is a highly relativistic object. So this is definitely non-negligible. So you see, from ordinary stars for a solar system, you have this 10 to the minus 6, to the white dwarf, the 10 to the minus 4, and to the neutron stars, say 10 to the minus 1. Only then for the black holes, to be discussed later, it's really 1. Now the radii of these objects, what's the difference here? Of course, you must replace here these expressions here. You must replace there the electrons by the neutrons. And if you do that, so the radii are, what you find is then, of course, then the instead of the electronic Compton wavelengths, the neutron one, and then alpha g to the minus 1/2, and rho 1 over rho to the 1/6, which gives you, because this is a factor of 1,000 smaller, it gives you roughly 5 kilometer instead of 5,000 times rho 1 over rho to the 1/6. No? And so you see, if you have the same mass and you go from a white dwarf to a neutron star, it becomes even denser. No? So it's unimaginable, I mean, how dense these objects are. And they are of the size of, say, Cologne or something, of a city. No? So the sun, if it makes a white dwarf, it's an order of size of the Earth. But if an object, and you need actually bigger stars or heavier stars to form neutron stars, they will be with the same mass, then at the end reach a city size. And you see, if you compare the size of this neutron star over the ratio of the radius of white dwarf, it's given by the ratio of the Compton wavelengths. So you see again how microphysics determines the size of stars. Not this simple ratio determines, I mean, the relative size of neutron stars and white dwarfs. Now, of course, there is a very interesting astrophysics behind all of that. Also, very interesting history. I mean, the white dwarfs, the first white dwarfs were discussed in the 19th century. Of course, it was not clear. The physics was not clear at that time with the companion of the star Sirius. Neutron stars were first discovered in 1967 in the form of pulsars, and so this is, it was and is still an active field of research in astrophysics, and I can only encourage you to read a little bit about the astronomical side of this, which we will not, because this is a relativity course, not follow here. But you see here how important relativity becomes for this, and how relativistic effects are determined by the physics of those objects. So far for today. So next time in 11.2 I will generalize, as promised, the equation of the hydrostatic equilibrium to the version that we derive from Einstein's theory. So it will be more complicated, but it can be derived because we can actually have an exact solution that is for a spherical symmetric object that gives you the interior solution of the exterior Schwarzschild metric. And we will also make in 11.2.3 some remarks on binding energies before we then come to the big part of black holes. So thank you again, and bye bye for today.